So today we're going to be looking at extreme values. Okay, extreme values. And extreme values are exactly what they sound like, right? They are extreme, right? So we're looking for things that are extreme in comparison to the other things that are around it. In particular, we're going to be looking for maximums and minimums. So things that are, a maximum and a minimum, they're very extreme in comparison to the other ones. Maximum obviously being the biggest number around, minimum being the smallest number around. And in this, we're going to talk about two different types, okay? This is just a little bit of information for you. There are two different types, okay, of maximums and minimums, right? There are local maximums and local minimums, and then there are absolute maximums and absolute minimums, okay? And you can see the definitions up here. So if you'll just follow along with me in these definitions, it says you have a local maximum at some point x, some value x, right? That x is equal to c. If f of c, and this is the thing that I want to emphasize, that is a y value. Okay? That f of c right there is a y value. So you have a local maximum at x, at some x value, if the y value is the maximum value of, and that right there is y value, again, y value, on some open interval. So literally, all that is saying is that you have a local maximum at some y value if it is the maximum, in other words, biggest y value on some interval. So it's a maximum if it's the biggest one, and that's literally all it means right there, okay? But notice that it's the y value that's maximum. It's not the x. There's nothing extreme about the x, okay? It's the y value that creates the extreme situation. The y value is a maximum. Or in this other case, this right here is again a y value, but this time the y value is a minimum. If it is the minimum, so the smallest value of any y value on some open interval. So it's a local minimum if it's the smallest one on some interval, right? Then we have absolute maximums and absolute minimums. And the only difference now is, a function has an absolute max at some x value, so it would be at that x value if this, remember again, this is the y value. If the y value is a maximum value of all the y values in the interval. And notice this one is of all, right? So the only difference now is that now we're talking about all. So if you wanted to think about it in terms of, celebrities, there are local celebrities, people like myself who are more popular than other people in Starkville, right? And then you have absolute celebrities, or another word that we can use whenever we're talking about absolute maximums and minimums is sometimes you'll see global maximums and global minimums instead of absolute, right? These words sometimes will be substituted for global. So you also have, in the same way that you have local celebrities who may be more popular than other people in some small area, right? Then you also have global celebrities. And global celebrities are more popular than most of the people on planet Earth right now. Some global celebrities might include someone like Rafa Nadal, right? An extremely famous tennis player who is known on a global scale, right? He's internationally known. Okay, other famous global celebrities like the Beatles, people who are known all around the world for their music, right? So they are more well known than anyone else, right? So while people who live in Starkville might be local celebrities, right? Guys like Mayor Wiseman, some Mississippi State football players, they may be local celebrities, but they're not global celebrities, okay? And so the same thing with these maximums and minimums. There are such things as local minimums, and then there are globals, okay? And here's a nice little picture for us to look at, okay? And you can see that this right here says that the graph below, I will use the graph below on the interval from -8 to 8, okay? So we're going from -8, that point right there is the definite endpoint, to 8, and that's a definite endpoint. You don't really need to copy this graph down in your notes, but I just want you to pay attention to what I'm looking at right here, okay? Remember, something is a local maximum or a local maximum, let's just stick with that one for now, if it is bigger than all of the things that are right next to it. So let me give you some examples of some local maximums. This right here is a local max, right? It's bigger than the ones that are right next to it, so that's all it needs in order to be a local maximum. Another local maximum is right here. If you notice, it's slightly bigger than the ones that are right next to it. So when it says some open interval, I don't want you to think that that interval has to be very large, right? This thing is bigger than the ones that are right next to it, so it's a local max. And so is this one. It's bigger than anything that's right inside that little, those little alleys that I made right there. So they're local maximums, right? They're bigger than the things that are right next to them. Now, when I get to this spot over here, yes, this is obviously a local max, right? But if you notice, when we talk about the Y value, and I just want to emphasize again that the Y value is what makes something an extreme value. If you look, that Y value right there is the highest point anywhere on the graph, right? So since that right there is the highest point anywhere on the graph, that's not just a local max, though it is local, right? Rafa Nadal is a global celebrity. If he lived in Starkville, he would also have to be a local celebrity, right? So he is more famous than everybody in Starkville, but more importantly, he's global, right? So this one right here would actually be the global or the absolute maximum. It's the highest one anywhere on the graph. Okay? And then if we look for minimums, right? If we come around looking for minimums, well, this spot right here is a local min. It's smaller than all of the other things, right? It's smaller than all of the other spots around it. And then this would also be a local min, right? It's smaller than everything that's around it. This here, this endpoint would be a local min. It only goes one way from there, but it's still smaller than all the things that are right next to it, right? Out there on the edge, it hits a definite smallest point, so it's a local minimum out here on this endpoint. But then our other endpoint over here, this spot is the lowest, right, of all the Y values. That Y value right there is extreme. The Y value is the lowest Y value anywhere on the graph. So this is a global min, right? Or absolute. Okay, absolutely the lowest place anywhere on the graph. Now, once again, I want to point out that it's the Y values that are extreme, right? What's extreme at this spot right here is not that the X value is 1. There's nothing extreme about that. There are plenty of X values that are bigger. Here's a 5 that's bigger. Here's a 7 that's bigger. Here's an 8 that's bigger. These X values, there's nothing extreme about X equals 1. In the same way, there are things that are smaller. There's -1, and then you get over here to -5 right there. So the X value is also not the smallest, right? So the X values are not what we're talking about whenever we talk about the extremes, okay? The extremes are the Y values. Either the Y value is very large or the Y value is very small, not the X's. The only thing we use the X's for, and you may want to write this down, is location, okay? X values tell us about location. If we say where does the maximum occur or where does the minimum occur, then its X value will be a marker, right? This maximum right here, this one that I've been talking about, occurs at X equals 1. At gives you a location, right? That's where it is. It's at X equals 1. But if we said what is the extreme value, well, in this case, that's the Y, which would be 4. So the extreme value would be 4, and it's located at X equals 1. Okay, so the actual extreme values are the Y's, and the X's are only used to give us locations. Okay, locations. And hopefully that's fairly simple to understand. Local max is just bigger than the stuff around it. Global or absolute max is bigger than anything else anywhere on the graph. Okay, and then minimums obviously would be smaller than anything around, or absolute global minimums would be smaller than anything anywhere on the graph. Okay, this is our first theorem, I think, that we've actually talked about in this class, okay? And it's called the extreme value theorem, the extreme value theorem. And it's fairly simple. You want to go ahead and copy it in your notes. But it says this. It says if f, so that's a function, we have some function f, is continuous, so it can't have any discontinuities, right? You got to be able to draw the entire function without picking up your pencil over a closed interval. So the interval has to be closed. Let me just make sure that we know that a closed interval looks like this. This goes from 3 to 5. And what this means is we actually touch the 3 and we actually touch the 5. So we go from definite points. So if you wanted to know what it would look like on these graphs up here, those endpoints are closed in, as opposed to an open interval, which would have parentheses. Those would mean that, if we had a graph, we would start at 3, but it would be open, and then we would go until 5, and it would be open, right? So this is an open interval. The endpoints, you don't actually touch the endpoints. So remember, the brackets actually mean that we're going to touch the endpoints, and the parentheses means that we're not. And so when we're looking for a closed interval, we want the brackets. We actually want to be able to touch the endpoints. And what this theorem is saying is that if you have a continuous function on a closed interval, then you have a guarantee, you have a promise that f has both a maximum value and a minimum value on that interval, okay? A maximum and a minimum. And so you can see several different examples here of what's happening. If you look at this first example here, you can see that it is a continuous function, right? And it is operating on the closed interval from a to b, so it does have a maximum up here and a minimum down here. Now the importance of the closed interval is actually shown in this second example right here, right? If these were open intervals, there would be nothing absolute that we could touch. There would be nothing that we could get right up to and say, hey, yep, we got there. That spot right there is exactly the maximum. With these open intervals, you can continue to get closer and closer to A, right? You could get closer and closer and closer to A, but you can never reach any point where you absolutely touched it and finally got there, right? So a maximum wouldn't be available in this case. But since it's a closed interval, right, from A to B, then we can actually get to this point. And so there is absolutely a maximum at A, and there is a minimum at B. Okay, so those endpoints can become very important, especially if you're dealing with something like a straight line on a closed interval, right? Those endpoints can actually contain your maximums and minimums. And then C, the third example here, you can see that there is, one of the endpoints is the minimum, but then there's this spot in the middle somewhere that's the maximum, which is fine. Okay, but remember, the extreme value theorem just guarantees, okay, it guarantees that so long as you have a continuous function and you're operating on a closed interval, then you absolutely have to have both a absolute maximum and an absolute minimum on that interval, right? So somewhere in there's got to be a maximum and a minimum. Now, I have this almost like a counter example up here, right? Does this function have absolute extreme values? Well, it's kind of a complicated answer, okay? So one of the things that I want you to note about the extreme value theorem is that it is a guarantee. If you have a closed interval and a continuous function, you have to have extreme values. But it does not say that if those things are missing, that if you don't have a closed interval or you don't have a continuous function, that you can't have maximums, right? So it doesn't say, all it does is promise that if those things are true, then you will definitely have maximums and minimums. You will have extreme values. It doesn't say anything to the contrary. It doesn't say that if those things aren't true, then you can't, okay? It just means that if those things aren't true, you no longer have a promise, okay? So you need to understand this as a promise theorem. It promises something if these two things are true. If those two things are not true, yeah, you could still have extreme values. You're just not promised anymore. Okay, you're not guaranteed to have them anymore. And this is a prime example right here. Because if we wanted to talk about a max, an absolute max, we're looking for an absolute max on this thing. We have one. That spot right there at the very beginning is absolutely a maximum. So I'm going to say there's an absolute max at x equals a, right? At our x value a here. That is the spot, that x value, where we have an absolute max. However, when we start talking about an absolute min, now I'm looking for the lowest point on the graph, the specific absolutely lowest point on the graph. And you can see that I'm going to call this right here point C, right? This part of the line right here is the lowest anywhere on the graph. There's nothing lower. But if you notice, there's an open circle, right? There's an open circle right there. And what that open circle means is that we can get as close as we want to that point, but we can never touch it. So what's going to happen is that minimum value is going to get closer and closer and closer and closer to this open circle, but never get there. So we don't have one specific number that we can say, that's the minimum, right? Because no matter what you think it is, if you get it really, really close to this circle right here, guess what? You can always get closer. You can scoot a little closer and a little closer and a little closer, and so your number gets a little smaller and a little smaller and a little smaller. And you say, I made it, but no, you didn't, because you can always get a little closer and a little closer and a little closer, and that y value gets a little smaller and a little smaller and a little smaller, right? So since this thing right here is operating with that open circle, there's no absolute minimum. It doesn't exist. Okay? There's no one specific number that is absolutely as low as we can go. Again, because we can just keep getting farther and farther down, closer and closer to that circle, but there's not one spot that we can hit and say we made it and now we can stop, right? We can always just keep getting closer and closer and closer, and so there's never one that we can say is for sure the absolute minimum, okay? So this is a good example of a function that does this function have absolute extreme values? Well, the answer is yes, it has an absolute max, but no, it doesn't have an absolute min, okay? And you can see it's not a continuous function, right? It's not a continuous function. And so it didn't meet what was needed in the extreme value theorem. So because it wasn't a continuous function, if you remember that was part of the extreme value theorem, continuous. Well, that didn't work out. So because it was not a continuous function, then we could not be promised, right? The extreme value theorem couldn't promise us a min and a max. But could there have been one? Absolutely. There ended up being a max. Even though we weren't promised one, we got it anyway, right? But we weren't promised a minimum, and we didn't get one. It didn't come through, okay? So that can always happen. Just because you're not promised, you could have one, so you need to go look for them still. You're just not guaranteed to get one. Okay? So here's another good example. We're actually going to talk about this function right here. A nice, easy little function. F of x is equal to x squared. But what I'm going to do is I'm going to talk about it on these different intervals, right? I'm going to talk about it on each of these different intervals. So the first interval will be from 0 to 2 on the closed interval. Okay, so 0 to 2 on the closed interval means this, that if we graph this function, and hopefully you know what x squared looks like, and we're going from x equals 0 to x equals 2, right? That's our interval, from 0 to 2. It looks something like this. And since I have these, closed intervals right here, I'm actually going to be able to touch both points. And so the maximum, hopefully you know, right at 2, our y value, remember the max is a y value, okay? The x value tells us where it is, but the maximum itself is a y value. So the max in this case, the highest that this graph can get, if we just look at this little piece, remember we're only looking at the little piece from 0 to 2. And so from looking at this little piece from 0 to 2, the highest that thing could ever get is 4. And then when we start talking about the minimum, the lowest that this little piece could ever get is 0. Okay, so then I'm going to change the interval on you, right? I'm going to change the interval. So now, we're not looking at this anymore. We're going to look at 0 is closed. Okay, so the 0 is closed. So I'm going to put a closed dot. But now at 2, we have an open interval, right? So we have an open circle up there at 2. So what this means is that now whenever we look for the highest point on the graph, we can get closer and closer and closer to that circle, and we can get closer and closer and closer to this point, but there's not anything that we can ever actually get to and say that we made it, right? And so if you said, oh, well, it's going to be 3.9999, well, guess what? We could get even closer to the 0.24, right? We know that this spot right here is 2.4. 2.4. You say, oh, well, it's 3.99, Mr. Williams. Well, not really, because you could always get a little closer. You could go 3.9999999. And then you say, oh, well, that's it. Well, no, we could always add a couple more nines on the back. And we could just continue that forever until we keep adding more nines and more nines and more nines. And that process could go on forever. And we could never actually reach one and say, we got there. That's the maximum, right? So this maximum does not exist, because it's on an open interval right there. But the minimum does. There's a closed circle. We hit 0, and that's as low as it can possibly go, so the minimum is 0. Now, in the next example, the 0 is open, but at 2 we're closed. Well, in this case, the same thing happens with the 0 now. If we got closer and closer to that spot at the bottom, we could continue to get closer and closer and closer. So there is no minimum point. Right? It does not exist. There's no spot that we could absolutely get to. But for the maximum, we know that 4 is absolutely as high as we can go. And now if we consider the last one where they're both open, so we have an open interval at 0 and an open interval at 4, well, now we can't get really close to either one of them. We can't say for certain that either one of them has an absolute max, right? Because we can always just keep moving closer and closer and closer and closer. Okay, so that's kind of the idea behind the extreme value theorem. Okay, that's the idea behind the extreme value theorem. You got to have a closed interval and a continuous function, and if you have that, you're promised. If you don't have it, then you're not promised anymore. Okay, remember, it could still happen. You just weren't promised any longer. And so we've actually been just looking at graphs and picking out, the extreme values. This is the highest point, this is the lowest point, and it's pretty simple. But now we're going to get into some more complex functions, right? We're going to get into some things that are a little more complicated. And so I just want to look at this right here, and I just want to try to make some general observations about what happens at any of these points, whether it be a maximum or a minimum. Right? Because there are 3 places where you can get an extreme value. Okay, so we're going to look at this picture, just make some general observations about the spots where extreme values occur, and we're going to come up with the 3 different places where we could actually get an extreme value. Okay, 3 different places where we could actually get an extreme value. Well, if you notice, this is the same graph as before. So we had an extreme value there, here. There was one up here. There was one here, and then one at the end. And hopefully from this last example that we did, right, where with this interval right here, the extreme values occurred at 0 and at 2, right, you can see that where they occurred was those endpoints, and you can notice that on this graph, this was the graph from -8 to 8, and so we had extreme values on the ends, right? Now, it's important to note that that was, a closed interval, because if it was open intervals from -8 to 8, then we could no longer have extreme values on the end, okay? But these endpoints are important. They're endpoints is one place where extreme values can occur, but they can't just be any points. They have to be endpoints on a closed interval. Okay? Endpoints on a closed interval. Now let me examine these 3 other places. I'm going to look at these 3 together. That one, and that one, and that one. Because those are all places where it's nice and smooth and the line just switches, right? It goes from increasing to decreasing, or from decreasing to increasing, but it's just like a nice smooth curve. You kind of either get a little hilltop or, a nice little valley, right? And there's something special about all of those points. Okay, here's what it is. The tangent line right there is horizontal, and the tangent line right here is horizontal, and the tangent line up there is horizontal, right? All of those tangent lines ends up being horizontal. And hopefully you remember what's special about a horizontal tangent line is that it's completely flat. So what that means is that the derivative is equal to 0, right? At those places where the derivative is equal to 0, you get those flat, those horizontal tangent lines. And so whenever you get those flat spots, right, that's where a maximum can occur. It goes up, flattens out, there's a max up there. If it comes down and flattens out and goes back up, then there's a minimum there, right? So you can see that these extreme values occur anytime that our line gets completely flat for a second. And so those are, the line's going to get flat for just a moment, and that's going to be, indicated by our derivative hitting 0. There are also a couple other spots. So see if I can back up to get some of these things gone. Okay, here we go. All right, so look at this spot here and this spot here. Those are the two other ones, right? We did the endpoints on the closed interval already. We did the flat spots, but hopefully you notice something special about those 2 points right there. Those are 2 of the 3 points on this graph where the derivative does not exist, okay? Because this right here is a corner. And this is a corner. Okay? The other thing that could happen is we could have a cusp. Hopefully you remember a cusp looks like this. Right? But that little spot down at the bottom of the cusp could be a minimum. Or if the cusp went the other way, right? The top of the cusp could be a maximum. So these little corners and these cusps right here are places where we can get extreme values. And so remember, those happen where the derivative does not exist. And so these are the 3 main places that we're looking for, where the endpoint's on a closed interval, or if the derivative is equal to 0, or if the derivative does not exist, right? Derivative equals 0 gives us those flat spots on top of a hill or in the bottom of a valley. And does not exist gives us those mountaintops, those high peaks, right? The corners that stick up and the really, really sharp valleys that stick down, right? So those are the different places we can get them. I want to make one more note, and that's that these 2 things right here, okay, where the derivative is equal to 0 and the derivative does not exist, have another special name. They're called critical points. Okay, so those 2 spots right there are called critical points. So if you ever see someone asking you for critical points, you see something in the text that talks about critical points, it's talking about those 2 things, where the derivative is 0 or the derivative does not exist. Okay, so now go ahead and write this example down. We're going to take this function, f of x is equal to 2x cubed minus 15x squared plus 24x plus 7. And we're going to consider it on the interval from 0 to 6. And notice that that is a closed interval, right? And so we want to find the extreme values of the function. Okay, we want to find the extreme values of the function. And I might go a little step further and just make sure I write down where they are. Okay? So, when we look at this, remember the extreme values can occur at 3 places. The endpoints, when the derivative is 0, and when the derivative does not exist. So what I'm going to be looking for is, places to check. I'm just going to make a little note right here. Places to check. Well, I already know 2 of them. The endpoints on a closed interval, right? So x equals 0 and x equals 6. Those are 2 places that I want to check because I'm looking for any extreme values in between 0 and 6, and it's also including 0 and 6. So I'm going to check those 2 spots and anything in between. So I'm going to take this function f of x and I'm going to get its derivative because hopefully you remember the only other places that we can learn about extreme values is either where the derivative is 0 or the derivative does not exist. Okay, so I'm going to start by taking this derivative and it gives me 6x squared minus 30x plus 24. And so now I'm trying to figure out, is there any way, I want to find spots where that derivative is 0 or it doesn't exist, because those are my critical points. There are going to be other places where I could get an extreme value. So, if you just look at this for a second, hopefully you can tell that there's no way to make this one not exist. Okay, this is a quadratic function. It's going to exist everywhere, right? It's going to be a continuous function. So our only hope in this one is to make this thing equal 0. So let's ask it. Hey, derivative, is there anywhere where you're equal to 0? So I'm going to use this equation right here to figure out if there's a spot where this thing's equal to 0. And if there is one, then maybe we have an extreme value there. No. I'm going to start by taking this side over here. And to simplify this problem a little bit, I'm going to factor out a 6. So if I take a 6 out of all of these, then that just becomes x squared. This is now 30 divided by 6 makes 5x. And then 24 divided by 6 makes 4. And that's really nice because now I'm just going to divide both sides by 6. It makes this 6 go away. And I don't need the parentheses anymore, right? The 6 isn't out there. And the other side's still 0, right? So that's a nice, easy little trick. If you can factor something out right there and then go ahead and divide by it on both sides, and it'll just disappear, right? Because 0 divided by 6 is still 0. Now this needs to be factored. So I'm going to factor this into 2 sets of parentheses, and I already have it set equal to 0, so that's nice. And so this will be x and x. So I'm looking for 2 numbers that can be multiplied together to give me 4, positive 4, and then add together to give us negative 5. And so the answer would be negative 1 and negative 4. And negative 1 times negative 4 is positive 4. And negative 1 plus negative 4 is negative 5. And so now what I'm going to do is I'm going to take each of these, x minus 1 and x minus 4, and I'm just going to set them both equal to 0. Because if either one of those comes out to be 0, then that means that the whole answer would be 0, right? So I'm just going to check them individually. And obviously, if you solve these, you would get x equals 1 and x equals 4. Okay, so these need to be added to my places to check. I need to, I have 0. I need to add in x equals 1 and x equals 4. All right, so those are my places to check. Now, remember, what makes a value extreme, okay, what makes something extreme is the y value, right? So that derivative, all it's done is it's told us where to look. If you want to find extreme values, you should look at these x's, where x is 0, x is 1, x is 4, and x equals 6. Those are places that you should check, okay? So what I'm going to do now is I'm going to start trying to figure out about the y value. So I'm going to take f of 0. And I'm going to take this function up here and I'm going to plug in 0, and that's going to give me 7. And then I'm going to take that function, and remember, I'm taking the original function because I'm concerned about the y values. The y values are what tells me about the extremes, okay? So I'm going to take that 1 right there, and I'm going to plug it in. So if you have your calculator and you want to plug it in, you can. You may be able to do the 1 in your head. Shouldn't be overly complicated, right? So if you plug in the 1, or if you're calculating in your head right now, then hopefully you're going to get 18. Okay, and now we need to plug in the 4. So I'm going to take my calculator and I'm just going to plug in a 4 for x. Cubed minus 15, 4 squared plus 24 times 4 plus 7, right? So I'm just going to take my calculator and I'm going to run that in. Raised to the third minus 15 times 4 squared plus 24 times 4 plus 7. Okay, and for this one right here, f of 4, I got negative 9. Just do some calculations, make sure I didn't make a mistake. Okay, it looks good. So 4 is negative 9. So I checked 0, 1, 4. So now I need to check 6, f of 6. So I'm going to do the exact same thing. I'm just going to take this equation and now I'm going to plug in 6. Okay. And that gave me 43. And I just, these other ones could be maximums and minimums, the ones that aren't the globals or the absolutes, but I just want to talk about the absolutes in this problem. So let's just focus on the absolutes. And if I asked you right now what the absolute minimum for this problem was, right? Remember, you're talking about the y value. So hopefully you can look up here and tell me that it's -9, right? So I'm going to say that there is a min of -9. That is the minimum value. And then I'm going to say this, it's at x equals, so now I'm given the location, it's at x equals 4, right? So when x is equal to 4, we got -9, and that's our smallest one, so we know that that's our minimum value. It's a minimum of -9 at x equals 4. And then we also want our maximum value, and if we look in this thing, our maximum here, the biggest of these y values is 43. So we have a max of 43, and it happens at x equals, this was x equals 6, right? So those right there are going to be our extreme values. Now I don't want to discount the f of 0 equals 7 and the f of 1 is equal to 18. Those could both very well be extreme values. However, we don't really have a way yet to classify if they're maximums or minimums. You're not advanced enough yet. But we'll talk about a way to do that in the days to come. But as for right now, we're satisfied just saying that this thing right here has a minimum of -9 at x equals 4 and a maximum of 43 at x equals 6. These other two spots, yes, they could be local extreme values. They can't be globals because they're already beat out, right? They could be local extreme values, but we don't have a way to check and see if they're maximums or minimums right now. So we'll just be satisfied with having our globals down here. All right, here's another one. This one says find the extreme values of the function f of x equals x cubed minus 9x squared plus 24x minus 10. And you'll notice on this one I don't have an interval, right? And don't let that bother you. We don't have to have an interval, okay? But if we don't have an interval, we're no longer promised extreme values by the extreme value theorem, okay? Those are no longer promised, okay? So we don't know for sure that we're going to have an absolute maximum and an absolute minimum like we did on the last one. On this one, we knew we had an absolute maximum and an absolute minimum because of the extreme value theorem. Now, we don't know that so much anymore, right? We don't know that for sure anymore. So what we're going to do is we're going to look for extreme values, but now we don't have endpoints on the closed interval, right? The three options are endpoints on a closed interval, derivative equals 0, or derivative does not exist. Well, since we don't have an interval anymore, that first option is just gone. We don't have any endpoints on a closed interval to check, but we do still need to check for our critical points, the ones that involve a derivative, right? So I'm going to go ahead and take the derivative. It gives me 3x squared minus 18x plus 24. And just like before, this one right here is another quadratic, right? So it's not going to not exist, right? There's not a place where this derivative will not exist. So that means that the only thing we need to check for is when this derivative might equal 0. So let's ask it. Hey, derivative, when are you 0? See if we can come up with some answers. Well, this one, just like the last one, conveniently has numbers that are divisible by 3. So I'm going to factor out a 3. So it'll be x squared minus, and 18 divided by 3 is 6x plus, and 24 divided by 3 is 8. 0. And now, like I did before, I'm going to divide by that 3 on both sides of the equation, and these cancel. So I get x squared minus 6x plus 8 is equal to, and 0 divided by 3 is 0, right? So I was just able to reduce this problem down without having too much trouble. And now this quadratic right here will need to factor into two sets of parentheses. So I'll have an x and an x. And I need two numbers I can multiply together to get 8, and then add together to get -6. So I'm going to go for -4 and -2. -4 times -2 is 8, and -4 plus -2 does make -6 equals 0. And once again, I just need to take these and set them equal to 0 individually. And so now if I solve, I get x equals 4 and x equals 2. So these are the points I need to check. Remember, these are where, so these aren't my extreme values. There's nothing extreme about having a 4 for your x value, right? But they're where really big or really small y values could happen. So I'm going to come up here and I'm going to put check. And I got 2 spots, x equals 2 and x equals 4. Okay. Other than that, I'm going to get rid of some of this other stuff on here. And now I want to find out about their y values. So remember, I'm going back to the original equation, because if I want to know about y values, the original equation is the place to be, right? So I'm going to go back to the original equation, and I'm going to ask it about when x equals 2. So if you have your calculator again and you want to plug in, we're just going to do 2 cubed minus 9 times 2 squared plus 24 times 2 minus 10. So f of 2 is, you can put that into your calculator really quick. So minus 9 plus 24. Okay, and I'm getting 10 whenever I do that. Okay, so when when x is 2, we get out 10. And now we need to check for 4. So 4 cubed minus 9 times 4 squared plus 24 times 4 minus 10. And for that, I'm getting 114. Okay? So now, this one's a little tricky. We can't know that these are absolute maximums or minimums anymore, okay? Because we don't have a closed interval. So what could end up happening, is this graph could do something, it could do this, and then it could come back, right? And so there is the chance that the graph could look something like this. And if this thing does continue forever, since we didn't have an interval where we cut it off, the interval cuts it off. And if we look at this little piece right here, on an interval, the extreme value theorem guarantees us an absolute max and an absolute min. But since we don't have an interval anymore, right, then what that means is there could be a side over here that just goes up forever, or a side over here that goes down forever, right? And if that's the case, there would be no absolute maximum or minimum, because those things would, continue up forever and ever and ever and ever and ever, and it would keep going and going and going and going. So there would be no maximum value you could reach, because it would just keep going up. And the other one could keep going down forever and ever and ever and ever, and there'd be no minimum value you could reach, because it would just keep going down, right? So since we don't have the extreme value theorem at play here, we're no longer promised an absolute maximum or a minimum, so we can't know if these are absolutes or not, okay? We can find if they're maximums or minimums. We just can't know if they're absolutes because of the extreme value theorem not being at play. So out of these two, if I was looking for a minimum, well, that would be the small one. There's a minimum of 10 at x equals 2. And then the maximum, well, that would be the big one. There's a maximum of 114 at x equals 4. All right? So those are my two extreme values for that one. Okay, so let's check this function. So we want to find the extreme values for f of x is equal to x squared minus 8 times the natural log of x. Okay, so we want to go and have a look at this one. So what I'm going to do, once again, hopefully you've noticed that there's no interval, right? So there's no need to check endpoints because we don't even have an interval. But we do still need to check for the critical points that can happen with the derivative. So we take the derivative and we get 2x minus 8. And then remember, the derivative of natural log is 1 over x. Okay, so if I wanted to clean this up. Okay. Now this one has added an interesting new element, because now there actually is a way for this derivative to not exist, right? There is a way for this derivative to not exist. Remember, anytime you get 0 on the bottom of a fraction, then you have something that does not exist. So when we start talking about this thing not existing, okay, this is really important. There's only one thing that you need to do. It doesn't matter what else is around it and what else is, going on in the problem. You get a function that does not exist anytime you get 0 on the bottom of a fraction. So all I have to do to figure out where this thing won't exist is I just go to my fraction and I look at the bottom. And anytime that bottom is 0, the function won't exist at that point. So I don't have to worry about all this other stuff that's around it. I just know that if that bottom is 0, it's all over. So I'm simply going to take the bottom of that fraction, which is x, and set it equal to 0. And luckily in this case, there's nothing to solve. This right here is where f prime of x does not exist, right? So that is a point to check. And it's really easy to find. Okay? That bottom is equal to 0. The other opportunity is if the derivative equals 0. So we'll say, hey, derivative, when are you 0? And this one requires a little bit of algebra. It's not overly complicated algebra, right? But this is how it goes, okay? I'm going to do 2x, and since this is a negative 8 over x, I'm going to add 8 over x to both sides, right? And these will cancel. So now my 2x is equal to 8 over x. And so now if I want to get my x's by themselves, I need to get this x off the bottom. That's always a key. So in order to get it off the bottom, I'm going to multiply by it on both sides of the equation. On the right-hand side, it'll cancel. And on the left, x times 2x just makes 2x squared is equal to 8, right? That right side is just an 8 now. And then I'm going to divide by 2 on both sides of the equation. So x squared is now equal to 4. If I take the square root, that means that x equals positive or negative 2. So now I have two other places to check. X equals negative 2. X equals 2. So I'm going to get rid of all of this stuff. I'm going to come back up here, and so now I'm looking for extreme values. So what I'm going to do is I'm going to go back to the original function, because remember now I'm concerned about y's, and I'm going to check these two spots out. So the first thing I'm going to do is take 0 and plug it into that function. Now the first part may be easy with the 0, but if you're not really good with your natural logs, then you may want to go ahead and plug this thing all the way in, right? So 0 squared, once you got 0 squared minus 8 times the natural log of 0. And you'll notice that it gives you an error, right? There's an error, okay? So what that means is that this thing right here does not actually give you an answer. So at 0, this thing doesn't even exist. So what does that mean? Well, it can't be a maximum or a minimum, right? We're looking for extreme values. So all we care about is a maximum or a minimum. You're like, oh, well, is this person a local celebrity or a global celebrity, or is they just like, are they a minimum? Are they not known at all? And it's like, that person doesn't even exist, right? If someone doesn't exist, they cannot be a local celebrity or someone who is just kind of unknown within the community. They can't be a maximum or a minimum. If there's nothing there, then you can't have a maximum or a minimum, right? So, and all we're looking for is the extreme value. So the fact that there's nothing there just means that that point is meaningless to us. We don't need it for anything. So now, let's check negative 2. So that's negative 2 squared minus 8 times the natural log of negative 2. And so now when you plug this one in, make sure you use that parentheses with the negative 2, right? It's negative 2 squared minus 8 times the natural log of negative 2. And once again, you get 9 real answers. So this one doesn't exist either. And the reason why we're getting these is because the natural log, in case you're wondering, it's impossible to get the natural log of 0 or the natural log of a negative number. So these things don't work either. There's nothing there. So now f of 2. So this will be 2 squared minus 8 times the natural log of 2. And now we're finally going to get an answer for those of you who are curious if this was ever going to turn out to be anything at all. And we get f of 2 is equal to negative 1.545. Great. F of 2 is equal to negative 1.545. But here's the kicker. What's the big question that has to be on everyone's mind right now is that a maximum or a minimum? And how in the world can we know? Right? Is that a maximum or a minimum? And how in the world can we know? Well, we don't have anything else to compare it to right now, right? On the other ones, we had these other points, and we could look at them and say, oh, this one's bigger, this one's smaller, and so it was nice and easy. But now we got this crazy number. We don't have anything to compare it to. Well, here's what you do. You just find something to compare it to, right? You don't have any other spots to compare it to right now, but if you want to know if 2 is a maximum or a minimum, right? If you wanted to know if someone was, the tallest person in the room or the shortest person in the room, and you have them outside of the room, right? You have them by themselves, and they're one of the two things. They're either the tallest person in the room or they're the shortest person in the room. Well, in order to find out, all you need to do is call one person to come out of the room, right? So if you're standing in the hallway right now and you have someone with you, and they're standing there and you're looking at them and they look like they're about average height, and you're just thinking, I don't know if they're the smallest person or the tallest person in that room. And you really want to find out, all you got to do is open the door, tell one person to come out. If the person who comes out is shorter than them, then they must be the tallest person in the room, because those are the only two options. They're either taller than everybody or shorter than everybody. So if somebody shorter than them comes out, they got to be the tallest person. If somebody taller than them comes out, then they have to be the shortest person in the room. So this is all we're going to do. We know about f of 2, so we're just going to call one more person out of the room. I'm going to call 3 out. So we want 3 squared minus 8 times the natural log of 3. So we're just going to get this one other number in this function. All we need is one more to compare it to. So 3 squared minus 8 times the natural log of 3 gives us this, 0.211. And that right there is a positive, and that's a negative. So what that automatically tells me is this one's smaller. So since it's smaller, we must have a minimum at negative 1.545, a minimum of, let me say this and get it said right so you can keep up with it. It's a minimum of, this is the minimum value, and it occurs at x equals 2, right? We must have a minimum value there. Okay, and that's a nice and simple check sometimes you can do if you're curious if what you have is a maximum or a minimum. Just test the things around it. If they're bigger, it's a minimum. If they're smaller, it's a maximum, right? Nice and easy. No need to overcomplicate that. Okay, I'm going to work a couple of examples out of your textbook now. They're going to come from page 223. So if you want to go ahead and flip to page 223 in your textbook to keep up, you're more than welcome to do that. So go ahead and flip to page 223. Let's see how we're doing on time. Okay, for the sake of time, I'm going to skip number 30, and I'll do number 32. I'll tell you what, I'm going to skip 32 as well. I'm going to go straight to 38 for the sake of time, and I'll do 38, 40, and then I'll see if I can get in 44 and 48 as well. Okay, so I might work through these fairly quickly for the sake of time. So I'm going to go straight to number 38. Number 38 says this. It says y is equal to 2x to the 5th plus 5x squared. And we're working on the interval from negative 2 to 2. So we only want stuff that's happening between negative 2 and 2. And already, because I have these closed points, this closed interval, I already know that 2 points I want to check are x equals negative 2 and x equals 2. And if you read the directions here, it's asking us to find the minimum and maximum of the function, okay, by comparing the values and the critical point at the critical points and the endpoints. And so we're just going to compare these and find our maximum and minimum. Okay, so those are 2 places we need to check. And if we're looking for other places we need to check, well, we need to check the derivative, right? So if we take this derivative, we get 10x to the 4th plus 10x. No way to make that not exist, right? We don't have a fraction or a square root or anything like that that can make it not exist. So what we want to do is we want to come and we want to actually look at when this derivative will be equal to 0. Once again, with this one, just like some of the other ones, I could factor out a 10 here. This is 10 times x to the 4th plus x equals 0. And if I divide by 10, you don't have to divide by that 10 right now, but you can just make this thing a little bit easier. Equals 0. All right, well, now I have two x's here, so I'm going to factor again, right? I'm going to actually take out an x this time. And you could have taken out a 10x to begin with if you wanted to, but this will be x cubed plus 1 when I factor out an x. And now since I have this equal to 0, I just need to take both of these things and set them equal to 0. So x equals 0. Well, that one's done. And then x cubed plus 1 equals 0. So x cubed is equal to negative 1. And then if we take the cube root of both sides, x is equal to negative 1. So x equals 0 and x equals negative 1. So we add these, x equals 0 and x equals negative 1. This is important. You always want to check for these values that you get and make sure they fall inside that interval, okay? So our interval is between negative 2 and 2. And so we're good because 0 and 1 are both inside of that interval. But if we had something like, say we found that one of these values was 3 right now, then we would just toss it out. We wouldn't even use it. We wouldn't even talk about it because this problem is telling us only to deal with the interval from negative 2 to 2, okay? And so these are the points we need to check. Negative 2, 2, 0, and negative 1. So I'm going to do these in my calculator really quickly, okay? I'm just going to use a little trick that I'll teach you guys when I get back. But I'm going to go ahead and find y of negative 2, y of negative 1, y of 0, and y of 2 as quickly as possible. Okay, so I already know what 0 is, right? So hopefully you can get that one. But I'm going to do these other ones hopefully fairly quickly. All right, I get negative 44 here. And then here I get 3. And then here I get 84. Okay? So those are the numbers that we get. And now hopefully this is a fairly simple process. That's the smallest, that's the largest. So we have a min of negative 44 at x equals negative 2. And we have a max of 84 at x equals 2. Okay? So now, make sure I go on to the right one. I want to go to 40, and then 44 and 48. So let's look at number 40. Okay, number 40 says this. Y is equal to 1 minus x over x squared plus 3x. Okay? And then we have an interval on number 40 between 1 and 4. Okay, so our interval is between 1 and 4. Well, we always want to check the endpoints on a closed interval, so we know we're going to use 1 and 4. Then we need a derivative, right? And this derivative does require a quotient rule, so we'll do low. D high is negative 1 in this case. Minus high, well, that's 1 minus x. D low, that's 2x plus 3. All over low squared, so x squared plus 3x squared. And now I'm going to simplify this thing down. Okay, it's going to make it a whole lot easier for me later if I go ahead and simplify it. So I'm going to distribute that negative 1, and it gives me negative x squared minus 3x minus, and then over here I'm going to go ahead and use my FOIL method. Okay, so it'll be minus 1 times 2x is 2x, 1 times 3 is 3, negative x times 2x is negative 2x squared, and then negative x times 3 is negative 3x, all over the bottom, which is squared. So now the top is x squared minus 3x. And now I'm going to distribute this negative, right? So that becomes negative 2x, negative 3, positive 2x, and positive 2x squared. That's 2x squared, and positive 3x all over x squared plus 3x squared. So y prime is equal to, okay? And now if I combine my x squareds, I just get a positive x squared. Here's a negative 3x, a negative 2x, and a positive 3x. Well, the negative one and the positive one will cancel. We just get negative 2x's left. And then minus 3. And I'm going fairly quickly here, so hopefully I didn't make a mistake. Let me come back and just kind of check through what I did again really quickly. Okay, for my derivative, low d high minus high d low. That looks good. So negative, negative, minus that stuff. 2x plus 3. Okay. All over x squared plus 3x squared. And so now we're looking for these critical points. And so our two options is for the derivative to equal 0 or for the derivative to not exist. Okay, and here's the nice thing about fractions. Okay, if the derivative is going to equal 0, okay, if the derivative is going to equal 0, or if a fraction rather is going to equal 0, what's on bottom doesn't matter. Okay, what's on bottom is not a big deal. If a fraction is going to equal 0, what's going to be important is that the top is equal to 0. So x squared minus 2x minus 3 is equal to 0. So the top would need to equal 0, right? So all I'm going to do is look at the top and set it equal to 0, because it doesn't matter what's on bottom. If the top is 0 in a fraction, then the answer is 0. So I'm going to solve this right here, and I'm actually going to cheat. This is, a little more complicated. So I'm going to use the quadratic formula. So if you have your calculator, you can just go into the programs section of your calculator and go down to quad form. Okay, and when you get to quad form, you just want to enter the coefficients. And so for A in this one, we have 1, and then for B, we have -2, and then for C, we have -3. And so what it tells me is that I get x equals 3 and x equals -1, okay? Now, I'm going to come up here and I'm going to add these. X equals 3, x equals -1. And this is the one thing I want you to notice about this. This x equals -1 is not inside there, right? We said we only wanted numbers from 1 to 4, and so x equals -1 is out of the question. So we just throw it out. We won't even use it. It's an imposter. It doesn't fit our standards of being in between 1 and 4. Okay, so that -1 is gone. Okay, so this was, I want to remind you, this was where the derivative is equal to 0. Now we also need to check for where the derivative does not exist. But hopefully you've known by now what will make the derivative not exist, right? What will make the derivative not exist is if the bottom is equal to 0. So now I don't even have to worry about the top. That's the nice thing about a fraction. If you have a fraction, then in order for the derivative to be 0, the top is 0. In order for the derivative to not exist, the bottom is 0. So all you have to do is set each piece equal to 0 individually and work with it. So the first thing I'm going to do to solve this is take a square root. And so that leaves us with just x squared plus 3x equals 0. Now over here I'm going to factor out an x. So x. And so if I factor that out, I'll get x plus 3 equals 0. And so now I have x equals 0 and x plus 3 equals 0. Well, this one's solved, and this will be x equals -3. So let me go back and add those two. X equals 0 and x equals -3. X equals 0, x equals -3. Well, once again, 0 is not in there. It's not in between 1 and 4. And neither is -3, so we throw it out too. Okay? And so because those didn't fall in that interval from 1 to 4, we don't use them. We only wanted to know about stuff in between 1 and 4. And so now we're down to those faithful 3, right, who actually fit all of the criteria in order to be considered for maximums and minimums. And so now we're going to find y when x is 1, y when x is 3, and y when x is 4. Okay? I'm going to use my calculator trick again really quickly and see if I can come up with these answers hopefully pretty quick. The 1 is pretty simple. If you plug a 1 into the top of this thing, you're going to get 0, so it ends up being 0. So for the other two, I'll go ahead and work those out. 3. Gives me -1/9. And then if I use 4, I get -3/28. Okay? Well, we already know what the maximum is, right? 0 is the biggest, so we have a max of 0 at x equals 1. And then for the minimum, which one's smaller, 1/9 or 3/28? Well, if you're not sure, you can take your calculator and have a look at it. But 1/9 is actually, in terms of absolute value, 1/9 is larger. So now that they're both negative, when you have a negative number, the bigger one is actually smaller, right? It kind of works in reverse. So in this case right here, -1/9 is the smaller of the two numbers at x equals 3. Okay, so -1/9 will be the smaller of those two numbers. Okay, so there's number 40. And now I'm going to go on to 44. Number 44 says this. It says y equals the square root of 1 plus x squared minus 2x. And we're going from 0 to 2. Okay, well, we know to check 0, and we know to check 2. So we need to take the derivative. So y prime will be 1/2, 1 plus x squared to the -1/2 power, times 2x minus 2. Okay, and now the convenient thing about this 1/2 power, right, is I actually want to send stuff to the bottom and tops of a fraction. So this 2 right here is on bottom, so I'm going to send it to the bottom of a fraction. This 1 plus x squared to the -1/2, well, since it's a negative power, remember I can send it to the bottom and make it a positive. So this is now 1 plus x squared to the +1/2 power on bottom. And then the other stuff I can send to the top. So this 2x would go to the top, and so would this -2 out here. So what I really have, and so all I did was just kind of split stuff into the top and the bottom, right? I want to make this fraction. Hopefully you remember the nice thing about a fraction is you can just set each piece equal to 0. So -2x, sorry, this will be -4x, won't it? So -4x over 2 times, and remember that's a square root, 1 plus x squared, right? 1/2 power is a square root. And so now if I'm looking for where it's 0, then I just take the top and set it equal to 0. Well, divide by -4, and x is 0. Well, I already have x equals 0, so I don't need that anymore. It's not going to help me. So this is where the derivative was 0. And now we need the derivative does not exist. Well, that means that the bottom of this fraction will be 0. So here it is. 2 square root of 1 plus x squared equals 0. So divide by 2 on both sides, and the square root of 1 plus x squared equals 0. Square both sides, and 1 plus x squared equals 0. That's not uncommon, by the way, to get some things where you keep getting 0 on the other side. It's actually really nice. Every time you keep, you divide by 2 and you still get the 0. You square it and you still get the 0. It's pretty nice. So now you subtract 1 from both sides. So x squared is equal to negative 1. You want to take the square root. So x is equal to the square root of negative 1. Well, that's an imaginary number, right? So basically what we did when we worked through that is we found, hey, there are no numbers, right? We didn't get anything that would make the bottom equal 0. So we don't have any critical points to report. We didn't find any. We went in search and we got imaginary numbers whenever we went looking for them. So we don't have any, and that's totally okay. There's absolutely nothing wrong with not getting any critical points. Okay, so there's not one that we can add to the list. Okay, well that's nice and easy, because now what that means is that all we need to check are those 2 points that we already had. So because we found a 0, which was already up there, we didn't add anything new. And then when we tried to make the derivative not exist, we ended up not finding anything. There were no numbers that we could, get for that. So now all we have to do is take these two numbers and plug them in. So y of 0, well, that would be 1, right? This would be the square root of 1 minus 0, so it would just be 1. And then y of 2, if we plugged in a 2, 1 plus 2 squared would be equal to 5 minus 2. So this would be 5, the square root of 5 minus, and then negative 2 times 2 would be 4. Okay, and so if you're having trouble looking at that and figuring out which one is smaller, then you can just take the square root of 5 and subtract 4 in your calculator, and it'll give you this decimal. Okay, the square root of 5 minus 4 is negative 1.76. Okay, so it's going to be a negative number, obviously, because the square root of 5 is going to be, smaller than 4. It would have to be, 16 in order for the 4 to end up being a 0. So now we know the minimum. The min is negative 1.76, and it's at x equals 2. And the max is 1. Max of 1 at x equals 0. So there are our extreme values. So now for number 48. 48 has some trig involved. Okay, so 48 says y equals x plus sine of x. And our interval here is from 0 to 2 pi. So we already know to check 0, and we know to check 2 pi. So now I'm going to take my derivative, and I get 1 plus cosine of x. And there's no way to make that not exist, right? There's no way for that to not exist. So what we have is that we want to check for 1 plus the cosine of x to equal 0. So I subtract 1 from both sides, and we're looking for cosine of x to equal negative 1. And now this is one where you just have to know your unit circle. Remember, cosine is our y values, and so, cosine is our x values. So we're looking for where it's going to be negative 1, and hopefully you know that's over here, right? When you go straight to the left, you get the point negative 1, 0. And so that's where cosine is going to be equal to negative 1. So what that gives us is x equals pi. You could also take the cosine inverse of both sides. So if in your calculator you wanted to do x equals the cosine inverse of negative 1, and hopefully if you have your calculator in radian mode, it'll give you 3.14. And maybe when you get that 3.14, you could deduce, that you have the, sine. So x equals, pi. X equals pi. So x equals pi here. Okay? And pi is in between 0 and 2 pi, so those are the places we want to check. So here's what we'll check. We'll check y is equal to x plus sine of x. And we want to check it at x equals 0. So 0 plus the sine of 0 sine of 0, not theta there, right? Well, sine of 0 is 0, right? Hopefully you remember that. So this is 0. And then y of pi would be pi plus the sine of pi. Well, the sine of pi is 0, so this will just be pi. And then y, if we check 2 pi, that'll be 2 pi plus the sine of 2 pi. And the sine of 2 pi is 0, so this will be 2 pi plus 0, which is 2 pi. And so here's our smallest one, it's 0. So we have a min of 0 at x equals 0. And then 2 pi is our largest, so we have a max of 2 pi at x equals 2 pi. So those right there would be our two extreme values. Okay, and remember this video is online, so if you didn't catch some of the stuff I did in class because I was going too fast, you can always go back and watch it at home at your own speed, scrub through it, find the ones you need to do, right? But this is your homework assignment for tonight, so go ahead and write those down out of the textbook, page 222 through 223. So those are the problems, or sorry, the same pages that I was working problems off of before. So hopefully you'll be able to use your notes in this video if necessary to get your homework done. And I'll see you guys again tomorrow.